Just notice that who is watching online and still wants to have a final grade, you should send exercises, okay, by email. Okay. It's okay. We don't expect that all of them are correct, but it's important to send what you can do. Good. So I recall briefly what we did. So we considered 1 degree of freedom system, 1 degree of freedom Lagrangian system. So which means that Lagrangian is kinetic energy minus potential, where x is a point on a line or an angle. And then we found out that the following thing. So we found out that, well, first of all, equation of motion was reduced to the form x double dot equal f of x, where f of x is minus 1 over m du dx. And this system can be described as a first order system x dot equal y dot equal f of x, right? So that's on a phase plane. xy or xx dot. So this is what we did. Also what we found, so that gives you unique solution x of t given initial conditions at some initial time, let's say time 0. So given the initial position and the initial speed, you have a unique solution at all times, not at least at nearby times. And then what we found out is that there are special points which are equilibrium. So equilibrium is when there is no motion. So it's a solution which is just constant. And this implies that there's a critical point of the potential. So derivative at this point should be 0. And then what we found is that everything, the local behavior, the local dynamics, the local dynamics correspond to delta x, which is x minus x0, and delta x dot, which is just same as x dot, right, are small. So small, local dynamics correspond to small distance to the equilibrium and small velocity. So you're just slightly near equilibrium and very slow. At equilibrium, you're exactly at the point and do not move, and nearby you slightly off and maybe it's very slow. So in that case, everything depends on the second derivative. I called it A. Today let's call it C, because so it depends on, so the first derivative is 0, so everything is depends on the second derivative, which is today we call it C. At x equals x0. So this C defines a local form first of all defines local form of potential, which we know is potential at point x0, and then it will be plus C over 2 delta x squared, right? It's a Taylor expansion and higher order terms. And in the same way, it defines a local form of energy. Which is conserved in the system, so it will be plus c delta x squared. So we can put delta here as well. That doesn't make any difference. And something of higher order. So that's our energy. And we immediately see, so m is positive, so local form of the energy depends on the sign of c. So that's what case 1. When c is positive, then the energy has a local minimum at the equilibrium. So x equal x0 and x dot equal 0. So that's energy is energy has a local minimum, so it's a place, right? So, and we know that energy is conserved, so the dynamics must be, all values should be at the level of the constant energy. Right? And we also found directly that on a phase space, what does it mean? So we have equilibrium. So all motions are the ellipse form of the ellipse, which is just local form of the intersection around the minimum. So that was case 1. So that case was described by the equation, approximate equation delta x double dot plus omega squared delta x equals 0. The square was c over m positive, right? And case 2 was the opposites, so c negative. In that case, the energy surface has a saddle point. The equilibrium. So that's our x0. And then it's saddle point. So it's now it's minimum with respect to velocity, maximum with respect to the speed. So with respect to velocity minimum, so it's poof, and with respect to the coordinates, it's maximum. So that's our point. And depending on the energy, so if the energy is exactly corresponding to that critical point, then the cut of such a surface is always locally looks like intersection of the two lines. If you go up, you will intersect it here, right? If you go lower, you will intersect it there. So different intersections give you different orbits, and this is in phase plane. This gives you different form of the behavior depending on initial conditions. So there was like this. So these are straight lines locally, or the curves which do not pass through the origin. So that's a local form of the saddle. This is saddle point, and the local equation which was describing this situation was just changing the sign, right? So sigma square was minus C over M, which is positive, no? Because C is negative. So that was the two situations we considered last time. And then also what we computed is we computed considering the periodic motion. So every closed curve defines a periodic motion. So starting from any point, you return to that point. So the periodic motion is a solution which has a property that if you add some given number t, which is called period, then it's the same value, the same point. So for all times and given so fixed period t bigger than 0. So t is a period. T capital is a period. So every time it repeats itself. So what we found how to find the period if we know the orbit. So what we found is that if you consider energy, so you do it if you consider energy to be constant, so if you consider energy as an equation with respect to x, given energy level, then what you can do, we derived that we expressed x dot, which is dx dt, and it was expressed from here as a square root of 2 over m e minus u of x. So that's function of x. And then I can write that dt equal dx over that square root. And that in particular gives us a periodic motion. So if you have periodic motion, so that arbitrary curve, it's always, in that case, it's always symmetric with respect to the x-axis. So there is a left point and a right point. Left intersection with an axis and right intersection. So you first cross from left to the right and then from right to the left in the same way, in the symmetric way. So then we found that the period is just you can find this interval between the 2 points, the time interval between 2 points, and then double it because it's the same from both sides. So this is what we found. So that was the expression for the period. So practically, having potential and knowing the initial energy, you can find this equation gives you the form of the shape of the orbit on phase space, and this formula, using the orbit, you find the period. So that's what we did. And in principle, that formula gives you implicit way how you connect position with time at every moment. So the second our interest will be, so the only part which remains still unclear are these straight orbits, these straight solutions. So you see there's a solution which enters the equilibrium. So it starts at a certain point and then it ends at the equilibrium, right? So what is this? What is the behavior along this line? So that's orbit. So we'll consider orbit, solution ending or starting at equilibrium. This solution they called this solution is called separatrix. So we will see the reason why it's called like this in a while. So separatrix. Actually, it separates different type of behavior. This we will see why. So let's just compute. So what we will do. We will start at some point, x1, t1, okay? And I want to compute the last point. So let's consider this point as x2, t2. So let's consider what happens if we start approaching this point. So what happens with the solution? So essentially, x, we know what happens with the time. So at what time t2 it reaches the equilibrium. How much time it requires to reach the equilibrium. So we do the same. So we use the same formula. We integrate it now from t1 to t2. So we take this formula. So we integrate from t1 to t2 dt. And then on the left, it's written next, so we integrate from x1 to x2. Oh, well, I forgot to write that this is plus minus, actually. But since we are going from upper side, it's plus. So what we want to see what is T2 as x2 goes to our equilibrium. So what happens if x2 goes to equilibrium? How much time it takes to come to the equilibrium? Okay, so how we do it? We use this formula that we know. Right? We use this formula. So we have energy. So first of all, we have energy. So we have energy, and let's just substitute this expansion. So m x dot square over 2 plus c x minus x0 square over 2. Right. So this is. And let's write it all together. Plus u. And now we keep the first term. Then it is ux0 plus c over 2 delta x squared. uf0 plus c over 2 squared plus higher order terms, right? That's Taylor expansion. This is exact relation. So what? And this should be equal to energy. It will equal energy. So first, we know we consider a solution ending at equilibrium. And at equilibrium, we have x equal x0 and x dot equal 0, right? So you just substitute these values here and find energy. So everything is 0. So this is 0, this is 0, this is 0. So what is left is that energy is just ux0, right? So that's what this expression takes. Okay, so now we know energy, and now let's compute the time. So the left-hand side will be T2 minus T1, right? And then we have to compute x1, x2, dx, square root 2 over m. So energy we know. So it will be u of x0. This is energy. And then we also know u, yeah, because we can substitute u. So minus u of x0 minus this term c over 2 0 squared so this is expression. We expanded potential energy. U cancels. So what will be? So there will be square root minus c over m, x minus x0 squared, q. So this is positive, right? C is negative. Remember that this is a situation when C is negative. So then this is positive, just positive number. We put it outside. We put it outside, so the end, what we get, t minus t1 equal c over m. So minus m over c, right? So we remove this coefficient. And also x minus x0, okay, let's keep it so far. Good. So x, remember now x is smaller than x0 because we're on that line. So x is from that side coming to x0. So we can also take out the square outside, but remembering that when you take it out, you should take positive value. So it will be, so it will give you minus. Will be minus x0. Like this. So I put minus here just to not to write modulus, but because it's negative, and then and then if you did calculus, you know that this is the 1 over square root of 1 plus small correction. You can write it as 1 plus small correction. Doesn't matter where you put small correction, it's always small. That's fact from calculus that I get. I think if you take course of analysis on the line, you will see it. So the result we have is like this, dx. So it's 1 over x minus x0, right? 1 plus 0 dx. And then we just take these terms separately. So first term will be dx x minus x0, and the second term, there will be, you say this will cancel, so it will be integral dx, and this is the integral on the finite interval. So this all is okay. So that's just okay. So that's it. Okay. So that's it. And this is a logarithm. This integral is a logarithm. So just remember that the integration of x minus x0 is so it's negative, right? So it's negative. Let's just put it right, so inside. So this is for you. So this is d log x0 minus x with a minus. So if you take table integral from this, is d in that. So we have put minus mc minus log x0 minus x between x1 and x2. And this is just some constant, and this is okay. And this is just numbers, just some constant depending on x2, which is which doesn't become big or small. This is just some number. And then let's put x2 here. So what you get at the end, so it will be minus. It's complicated derivation, but we are coming to the end. So we're coming to the end because now take the limit. We want to consider, we'll see how much time it takes to reach the equilibrium. So we put x2 closer to x0. So what you have? So the only piece where this x0 just changes this value, but here it's important because as x0 goes to if the approach logarithm goes to minus infinity with a minus, so it gives you infinity. So t2, and this is t2 minus t1. T2 is defined by this term because all other terms go to some finite values, and this term diverges. So that's important. So it takes infinite time to reach equilibrium. And this way, essentially, this is actually a rigorous proof because we always kept the correction in exact way, so that there is no approximations here. So we found that whenever you consider any of these solutions that ends at equilibrium, actually it never comes directly to that point. It just approaches the point as time becoming bigger, larger and larger, and it just approaches and comes to the point only at infinite time. So you can have the same calculation, but with line which is starting at equilibrium. So you can just show that it's actually, if you consider any point on that line and go backwards in time, you need infinite time to reach equilibrium. So these actually are 4 different. It's not one solution. These are 4 different solutions. 4 different solutions because these 2 solutions that end at equilibrium at infinite time, and these 2 solutions they started at infinite time. So that's a property of the separatrix. So it's a solution which starts or ends at equilibrium, and it takes infinite time to get there or to start. So in other words, actually this picture are 5 solutions. So I was wrong. 5 type of solutions. The 2 solutions which enter, 2 solutions that exit, and 1 solution that stays in the middle. So there is also equilibrium. And generally, this is generically this is all what you can get for the one-dimensional 1 degrees of freedom system. So what we can do now is to see how qualitatively we describe all the solutions. So what we do now is we construct a general phase portrait of 1 degree of freedom system, Lagrangian system. I will show you an example. Then we do it for the pendulum, but you will see that it's general. So everything in the one-dimensional 1 degree of freedom system depends on the potential. So we will, how we proceed, we take potential, which depends on x, potential energy U, and consider some particular case. So we will consider potential energy, which has such a form. So double well, the 2 minima, and then it goes to some constant, for example. And here it goes up. So everything depends. First of all, we define critical points. So this is minimum or maximum, because every critical point is the equilibrium. So for example, for this shape, we have 3 equilibria. Like 2 minima, which we know is stable equilibrium, and maximum is unstable. So this is a situation with the minimum. This is an equation with the maximum potential energy, which gives a saddle for the energy. And then below, you can draw the phase portrait. So what we do? So we first of all, we know that minimum is here, maximum is here. So all of them are. So we found already 3 solutions. So these points are solutions. It's just solution which stays at the point forever. And now what we will do, we will consider different energy levels. So different values of energy, and for each energy we draw what is the corresponding solution. So we will consider first energy level. So we consider all typical situations. So one typical situation is the energy level which is bigger than this maximum, smaller than that. The next will be which is in the middle, so which is bigger than the 2 minima, and then smaller than the maximum. The next will be, so we put this constant, so let's also draw the line which is above the maximum but below the constant, and then finally the line which is above that constant. Okay, so that gives us 3 levels of energy. E1, E2, E3, E4. So 4 levels of energy, and we draw the orbit. So the first is just slightly above the minimum, and we know that when you're above the minimum, the orbit is a closed line, which is approximately ellipse. So it's the energy. This is level of energy, and energy. Remember that energy is mx dot square over 2 plus u, which means that u of x is always smaller or equal than E. So if we say that energy of our system is here, that we can only be in this interval, because potential energy should be smaller or equal. So and this gives you the orbit. So it's right and below it's left. Because x dot should be positive here, x dot should be negative there. So now, essentially the same thing happens in the blue line. This is a limit. But with the same energy, you can have also motion around the other equilibrium. Okay. Then, I forgot. Let's draw also the line. So it will be 4 and 5. Let's draw line E3, which goes exactly through the maximum. This is an important line as well. So when the energy exactly at the maximum, it's exactly citation of the separatrix. So that will correspond to the all solutions which has energy at the unstable equilibrium. And we know that there are 5 of such solutions close by. But this solution which comes out, it's actually closed. And from here. So this is unstable point. There is solution going out. This solution getting in. It's actually the same solution. Let's make a loop. And also there is a solution that coming out at minus infinity time, but it's the same solution as the one that comes in. So the next solution will be this yellow line at E5. But you see now it's a closed orbit between that point and this. So it will be just single periodic solution. And then there is a solution which only has a left limitation, but not limited on the right. So then it will be something like this. So that's it. So we found qualitatively everything what can happen in the system just by looking at the potential energy and essentially by looking at the positions of its special points, which maximum, minimum, and behavior, how it behaves at infinity. So whatever shape of the potential function you have, you can define what happens. And at that moment, you can see why we call this curve separatrix. This is separatrix because it separates 3 regions of different behaviors. So one behavior is inside. It's all oscillations around the right fixed point. Then it separates all the behaviors which turn around the left fixed point. And the third is outside are the oscillations around two fixed points together. Yeah, so that's the meaning of the name separatrix, because it separates different regions in the phase space which are given by different behaviors. And this is pretty much the general situation which you can plot for different shapes of the potential functions. This will be one of the exercises. So given different potential functions, just you will plot different phase portraits. I think it's instructive to do this for the pendulum, because pendulum is our first examples that we always consider. We will consider different examples as well, but pendulum is certainly is most charismatic case. So pendulum. So what we have with the pendulum, the potential energy for the pendulum. So remember, the potential energy for the pendulum as a function of the angle is mg of the height, and height is L 1 minus cosine phi, right? So and this means that we better put origin, and then angle of the pendulum is changes between minus pi and pi, or you can just continue it periodically. That's our pendulum. So this is where it stays straight, it's phi equals 0. When straight up, then phi equal pi or minus pi, right? Depends. So the potential energy is 0 here, and it gets maximum at P. And continues periodically. So then it's just the same. You can continue periodically as much as you want. Okay, so now we can draw phase space. So it's not x, it's phi, no? Phi dot. So we know this is a minimum. This is a maximum. This is a different fixed point. Now the separatrix is the orbit which corresponds to the energy exactly at the maximum. So the situation with the pendulum is that the same energy is at both pi and minus pi positions, because it's just the same position. So the separatrix that should be here, if it exits this point, it's exactly the same as enters that point, because they have the same energy. The separatrix correspond to the energy level going from maximum. Generally, all maxima at different level, but in pendulum, these maxima at the same level because it's just the same position. So the separatrix exiting from here should enter in that point. And actually, this is the same point, because this is the pi minus pi.
Isn't that minus pi?
Minus pi. Very good. So you follow. And then the same, it's always symmetric in this system, and so on. And then it's what continues in both sides is just same copies of the picture, right? Because it's periodic. Good. And now we have the energy level which is below, and it corresponds to the periodic motion. And there is a energy level which is above. Let's put this was red. And the energy level above here, and it corresponds to these kind of curves. And now we can see what every position means. So the blue behavior is just oscillations. It's a pendulum which oscillates around the local equilibrium. Just go so left, right, left, right. So now this curve, which you see it never ends, it just continues. These curves corresponds to the pendulum which just rotates, right? So here it rotates on a clockwise, anti-clockwise direction, and here it rotates a clockwise direction. And then separatrix correspond to the behavior when the pendulum starts at t minus infinity. It starts in the upper position at rest, then make one turn and ends again exactly at the upper position. Like one turn, and t equal plus infinity, it returns to the position. So that's separatrix, and that does the same but in different directions. So so you see that all behaviors we can see, and we can completely understand them, compute period, and all what you want. Good. Okay. So that's. I think we can make an interval. Let me see if. Yeah. So let's make a short break. Okay, so let's continue. So this second topic that we shortly consider is the 1 degree of freedom system with dissipation. So this is one of the type of the which we classified as large class of external type of forces, but this is specific force which corresponds to the dissipation of energy, which is usually present in any system. It can be small, it can be neglected, but it may be not so small. So let's consider our system with dissipation. So what it is. So remember, so this is a system with dissipation is formulated. So 1 degree of freedom. So it's the same. The same form as. So this would be the Lagrangian, the Euler-Lagrange equations. So this is Euler-Lagrange equation for the Lagrangian function of the system. Right? And then we should add dissipative force, which we know that it should be given as d of or d times x dot. So let's take in this form. So where d is some positive number. So in general, this is a matrix, right? But 1 degree of freedom is a number. Okay, so what is different in this case? So first thing that we already computed, that the derivative of energy will be minus dx dot squared. Right, so this is what we computed before. We computed in more general form. It's when d is a matrix, but when one dimension it's just this. You can compute it directly from this equation if you like. And this is always negative if x dot is not 0. So whenever there is motion, energy decreases. So energy becomes smaller and smaller. So certainly what it means for the phase portrait is that you never stay at the same energy line. You always go to smaller energy. So from this you go to smaller, to the smaller, to the smaller, to the smaller, to the smaller, smaller. And of course, what you can see from this picture, for example, if you start some point here, you always will go to the smaller energies. And certain moment you intersect separatrix, either in this region or in that region. Whenever you intersect in certain region, you cannot exit from this region anymore. So at the end, you will fall to the minimum of energy to this local minimum. So essentially the idea is that we have the energy, which we can define in the same way. It's function of position and velocity, and it's certain surface. You start at certain point, position and velocity, and then you move. But you always move in a decreasing energy. So unless you, as far as you're moving, you never stop. So you can only stop. So well, This is what we have to see. So whenever you're moving, so you move generally until, so you're always going down. So you're only limited by the minima of this function. Right? Okay. So the situation is essentially the same. So what will happen on the phase diagram? Phase diagram, you just go from one. You just the curve will always just go from in the direction of decreasing the energy, and the behavior will be. The only thing we should understand is what will be behavior near the minima. So what will be local behavior near the minimum. So how it will enter to the minimum, and if it will enter at all. So let us analyze this system near the equilibrium. So dynamics near equilibrium. So again, what is equilibrium? It's solution which is constant. In that case, x dot, the velocity is 0. And you see velocity is 0, acceleration is 0, so it's just the same condition that it's critical point of the potential. Okay, equals 0. So equilibria are not affected by damping. You put damping, equilibria are just in the same positions. So now near the equilibrium. So near equilibrium means that our coordinate is close to the equilibrium point, and also our velocity is close to 0. Are small. And we already know that whenever it's small, we know that this part, the left part, can be written as m, the acceleration plus c delta x, where c is second derivative. So this is this piece where we know, so we only need to add that piece. And we can put delta because for the derivative it doesn't matter, with coefficient d. So this is our equation for the near the equilibrium, but for the damped system with the damping, with dissipation. So again, we have two cases. So the important case will be case 1 in this case. So case 1 is C positive. C positive means that the equilibrium is a minimum, this minimum or this minimum. So it's minimum of the energy, and in that case, so what we do, we define omega square as C over m. It's positive, and also we will define gamma as d over 2m, which is positive. And then you define everything by m, and the equation will be, put this to the left, it will be plus 2 gamma delta x dot, and this will be plus omega square is equal to 0. So that's equation near the equilibrium. So I just divided by m, so c by m gives you omega squared, and d by m gives you 2 gamma. Do you agree? Okay. So now this is not so simple equation as we had before. So how you solve this equation? You solve this equation by two tricks that we will use a lot later. Is that you notice that this is a real linear equation. Right? So it's for real coefficients, real functions, and it's also linear. The delta x enters only linearly. And this gives you two properties. The first property, that if delta x of t is a complex solution, so complex valued solution, then real part and imaginary parts are also solutions, which are real now. So this tells you that in principle you can consider complex valued solution. This is okay. If you consider complex valued solution, which you substitute it solves the equation, you get automatically two solutions, because its real part is the solution, imaginary part of the solution. Just taking a real part of equation, it will be satisfied by it will be the same equation satisfied by a real part. Imaginary part of this equation will be the same equation satisfied by imaginary part. And the second property is that if we have two solutions, are solutions, then any linear combination is also a solution. For any C1, for any coefficients. Yeah? So linear combination is also a solution, because if you take combination, this equation can become sum of the two, each of them satisfied, and this gives you a solution. So these are two properties that are always satisfied by any linear equation with real coefficients. Okay, so now what we do is that we use this property. And we consider delta f, we look for the solution of the form, so it's just particular solution of the form delta x of t equal exponent lambda t when lambda is complex number. So, okay, let's just guess solution in this form and try to find lambda such that it satisfies the equation. So you substitute it here. So double dot gives. So remember, when you differentiate exponent, you get lambda. So second derivative will give you lambda squared. First, then will be 2 gamma, and first derivative gives you lambda, and then omega squared e lambda t. Okay, exponent is non-zero, so we can cancel it out. So we get lambda squared plus 2 gamma lambda omega squared equals 0. So this is quadratic equation. And then you find that lambda is minus gamma plus minus square root of omega squared. So you find the two roots. So there are two subcases. Two subcases correspond to the two situations whether it is positive or negative. So we can have a subcase. So it will be 1a, right? 1a will correspond to the case when gamma is smaller than omega. So when the dissipation is not that so weakly, so dissipation is weak. So it's smaller than some value. Gamma is smaller than omega. Remember, so what it means? It means that d by 2m is smaller than square root of c over m. So that's a full condition. In that case, if gamma is smaller than omega, in that case this is negative. So the square root is imaginary. So then we can find, you see that lambda is minus gamma plus minus imaginary unit by omega capital. So omega capital is square root of inverted relation. And you can see from here that omega is bigger than 0 and smaller than omega. Correct? And the solution that you get, the complex solution, is, so let's take one of them with a plus. So when you take it with a plus, it will be exponent minus gamma t plus I omega t. If you take with a minus, at the end you get the same result. So what it is? So this is, remember that complex number, so this is minus gamma t, which is a real part, and then there will be cosine and sine. Good. And now we remember that real parts of this solution give you a solution, and imaginary part give you a solution. So we get two solutions. So the first solution will be minus gamma t cosine omega t, and the second solution will give you exponent minus gamma t sine omega t. And the final, we use the first property that we can split any complex solution to real part, imaginary part, gives you two real solutions. And then we can use the second property that any linear combination again gives a solution. So then you can find the solution, which is so E minus gamma t, and linear combination. So it's the same prefactor. So we take linear combination A cosine omega t plus B sine omega t. For any numbers, this is a solution. So now it remains to check that this is actually general solution. So this is a general solution. How you check it, you have to verify that you can satisfy any initial condition. So given initial condition, so let's take given initial deviation and initial velocity, how you find the solution. So first compute this at t0. So at t0, this is 1, this is 0, and this is 1. So we find A. A is just initial position. And the second, if you compute derivative. First, let's compute derivative in the general. So this is, you have to differentiate with respect to time. So first, taking derivative of the exponent gives you minus gamma. And then you take derivative of these functions inside. It gives you A minus A omega sine omega t plus B omega cosine omega t. And then we compute the same derivative but at initial time. So this gives you 1, so it will be minus gamma A. This gives 0. Plus this is 1. This is 1, so B omega. And here now we find B. So now remember this is x0. So we find B equal what will be on the left. Divided by omega. So we really see that whenever you give initial condition, initial position and speed, you uniquely define A and B. So and with this A and B, you have a solution at all other times. So it is really general solution. And what this solution means is that on a phase space with the equilibrium, so what you have? You have the piece which is the same piece as we had, is just a motion along the ellipse, but there is prefactor which exponentially going to 0. So, but it never 0, so it only goes to 0 exponentially at infinitely large times. So the local behavior is that you oscillate, but every time exponentially approaching 0. So this is a situation where dissipation is not that strong, right? So dissipation is not that strong, and so that instead of making ellipse, it's just going close and close and close until it reaches at infinite time the equilibrium position. Okay, so this is case A. So the case B is opposite. It will be subcase 1b. Well, that's just vice versa. So gamma bigger than omega. So it's kind of overdamped. So the damping is strong. If it's strong, then this square root is now real. So but it gives two real values. So it's just one with a plus, another with a minus. So what we can do, we define, so now we have lambda equal minus gamma plus minus, the square root we call sigma. So sigma will be square root of gamma squared minus omega squared. And what we know is that it's between 0 and gamma, right? It cannot be bigger than gamma. So there are two roots actually. There is lambda 1 minus gamma plus sigma, and lambda 2 minus gamma minus sigma. And they both real and negative. You see, even if you put plus, it's still negative. So what happens in that case? Okay. So now we don't need to put real part, imaginary part, because everything is real. But we do have two solutions. So we have so general solution can be constructed as a linear combination. So coefficient A by solution with lambda 1. And the coefficient B with the solution number 2. So you can check as an exercise that you can, given any initial condition and initial speed, you can take uniquely A and B that satisfy. You can check it already as an exercise. just in the same way, but formula will be different. And but behavior is different in this case. So when you take point x0, so what you see? So you see that as time goes to infinity, both solutions go to 0, but then do not oscillate. And this goes faster. So at the end, you will have this solution, this piece dominating the whole solution. This piece will dominate the whole stuff. And how it will go to 0 will depend on coefficient A. So essentially, for example, if you start some point here, poof, you will enter the equilibrium, but without any oscillations. So this is over-damped decay, exponential decay. So you see that if damping is strong enough, you don't see any oscillations anymore. So this is the second case, and so this is case B. And then we can also, in principle, consider the case C, or case 2. So the case 2, let's just put it here. Case 2 is correspond to C negative, remember? In that case, positive value will be with a minus, so this will be our sigma squared. We can keep still the same gamma. So the difference will be that we have minus sigma squared here. We still have the same properties, which we will not need, which still have the same derivation, but now with minus sigma squared. Will be minus sigma squared here. There will be plus sigma squared here. And this gives you two different lambdas. So there will be one lambda with a minus, which is negative, and another lambda will be with a plus. So you can see that this is bigger, so it's positive. And the general solution is delta x of t is a linear combination of the two. So now if you notice that this is in principle very close to what we had before. So you see, this is essentially the same as we had without dissipation, when gamma is 0. So there were two exponential terms, one with a positive value exponent, another with a negative exponent. So in the case 2, you don't have much of the difference between the damped and non-damped case, because the picture will be just the same. So it's the same saddle point in a phase space. So there is no, when you add dissipation on this case 2 with negative c, the phase space, the phase diagram doesn't change. It deforms, but qualitatively it's the same. So let's just apply all this, what we have, to the case of the pendulum. An example, and this will end the 1 degree of freedom case. So example, pendulum. So again, so we remember what this pendulum is. Okay. So let's recall that kinetic energy is ml squared phi dot squared over 2. So this is kind of our mass. U is mgl 1 minus cosine phi. Equilibrium we already computed. It's mgl sine phi, so it's 0, which means that there is equilibrium at 0, and there, which is straight position and inverted position. And then we also found that second derivative, right? So second derivative of u cosine phi. So in that case, you see, so in the first case, C is mgl positive, so we have stable situation. In this case, C is minus mgl negative, so it's unstable, so stable, unstable. So let's now just and the equation with the dissipation, which you have is so equation of motion that we had before is mg L sine phi. So this is Euler-Lagrange equation with 0 will be Euler-Lagrange equation for our pendulum. And if you put dissipation, you put minus d phi dot here. So this is our dissipative term with d positive. So this kind of friction, for example, it's either describes friction in at the upper point, or if it's there is air, or if the pendulum is in water. So that's resistance of the medium. Good. Okay, and we know that in unstable equilibrium there is no big at least no big qualitative change. So we only consider the stable equilibrium. So near equilibrium phi 0, what we can take, we take the instead of this we take c by phi, which is the same as expansion of phi. Right? So I substituted sine by phi. This is exactly our approximation. Because remember, this is mass by phi double dot. This is c by phi. That's what we did. Now let's divide everything. So we divide by ml squared. And this gives you phi double dot plus, I call it omega square phi. No. Let's put everything to the left. It will be plus 2 gamma phi dot omega square phi equals 0. So this term comes from here. And gamma is d divided by ml squared. D divided by 2 ml squared. That's it. So case 1a correspond to gamma smaller than omega. So this is when you have oscillations. And case 1b corresponds to case gamma bigger than omega. So when dissipation is weak with this condition, then you have damped oscillations. When the dissipation is strong, you have over-damped situation where there is no oscillations. So now let's, just to end this example, let's draw the phase diagram. So we start with the potential pi minus pi. This exactly the same value at the top. So no dissipation, remember, so first of all, so these are equilibrium. So in a case with no dissipation, we had this, we had such a picture, right? So this is when gamma was d equals 0, gamma equals 0. Now, at the moment we had, so the yellow is gamma equals 0. So now the next case will be red. Better. The red will correspond to gamma bigger than 0 but smaller than omega. So in that case, starting with at any point, you always go in the direction of decreasing energy, but you always oscillate, exponentially approaching the lower position. So the pendulum will, even if you start with rotation, it will start rotating slower until it crosses the separatrix. Crossing the separatrix, it doesn't oscillate, doesn't turn anymore, so it just starts oscillating, and it does slower, but never stops oscillating. It just goes to 0. And the different situation is over-damped case, when gamma is bigger than omega. So dissipation is stronger. So you start with the same point. The energy decreases faster, and you enter the origin without oscillation. So you can sometimes make a half oscillation. So it's sum of the exponents. So they can cross 0 once, but no, not more. You come to the 0. So it means that somehow intuitively, for example, if you take pendulum and you put it in the air, it has oscillation, and so it stops slowly, but oscillates. But if you put it into the oil, so the oscillation become much bigger. So now it will just relax without making turns. So that's a difference, and you can completely characterize it in that case. So this is a one-dimensional, one degree of freedom system where we can essentially understand everything from a qualitative side, for sure. So now we go to the second topic, which is system with many degrees of freedom. Have some time just to start. And of course, this is our main goal, general systems. First with many degrees of freedom, which is theory of oscillations, and then with infinite number of degrees of freedom, which will give us This is the waves theory. So systems with many degrees of freedom. So there are n coordinates. So first we start with Lagrangian system. So first we consider Lagrangian system, and we know that Lagrangian function of the system, so we consider the system which is isolated, or at least it can be written in Lagrangian form. So Lagrangian form, which only depends on coordinates velocities, and we already learned that this is kinetic energy, which can be generally written as, so that's as a sum of mass coefficient, generalized mass coefficient, which generally depend on positions by velocity and by product of velocities. So this is kinetic energy. And then there is minus potential. So this is general form of the Lagrangian. And we know another property is that m coefficient, they're symmetric. This is very important. So now we need to find the Euler-Lagrange equations. The general form is this for all I. So we never wrote this equation, so let's do it. Never wrote them explicitly, so let's write them explicitly. I think we have time. So let's compute every term. So let's start with this term. So dl dqi dot is dqi dot. So derivatives only come into the first term, so we only keep this term. 1/2 sum gk equal 1 to n gk q j dot q k. So how you differentiate? You differentiate this term when j equal I, and this term when k equal I, right? So the derivative is not zero when j equal I, then you just remove this, and k equal I, you just remove that. So there will be two terms. So when j equal I, you just keep k, and j equal I, so it's 1/2 m. So j equal I, so I k q k dot. So this is what remains when you differentiate the first, and when you differentiate the second, it's just the same but with j. So now you can, so in this sum cases variable that you sum, you can just replace j by k, k by j. So this will be sum 1/2 sum. So it will be m I j q j dot, and then we can just put this together. Next, you use symmetry. So this is the same thing, right? Because mij equal mji. So this cancel half. Okay, so we found derivative. So next step, finding time derivative. Mij Q J dot. Well, you differentiate by time the velocity and coordinates. So we start with the velocities. And then it just gives one more point. And then you differentiate coordinates, so you need to make this chain rule with respect to every component. So it will be plus sum, and so you add one more integration, or one more summation with respect to k. So you get d mij d qk, and then you get qj dot qk dot. Good. Okay, then we need this. So this enters this q here and then q here. It will be 1/2. And then here you differentiate all the, yes, minus du. So taking difference, you get equation of motion. So the Lagrange equation will be sum j equal 1 to n ij q j double dot plus double sum, and then here will be this minus half of this, which is different derivative. And then that with plus. So that's equation of motion. So we now wrote it in a full form, explicitly. Good. So first question is the same. So now what I said that we still know much about this kind of equation, but there is no general theory. You cannot just say describe all the solutions in a qualitative way what all the solutions that this equation has. Certainly you can solve it numerically, but this does not give you that much of the view. So the theory is well developed but not complete. So what we certainly can do is consider equilibrium. So oscillations near the equilibrium. Equilibrium is a solution which is constant. So some constant vector. Remember that we are in n-dimensional space, so it's a vector. So whenever we have equilibrium, all derivatives are 0, of course. So q dot is 0, acceleration is 0. So all these terms cancel. So what you have is that you find that if the point is equilibrium, that all first derivatives of the potential should cancel. And actually, this is in both sides. So if they cancel, then then this is also a solution. So the equilibrium is a critical point of the potential. So whenever you think of equilibrium, it should be critical point of the potential function, potential energy, so all derivatives should vanish. Okay, so next step is just the same as we did with 1 degrees of freedom system, is considering behavior near the equilibrium. So small oscillations near the equilibrium. It means that Q is close to Q0 and derivatives are close to 0. So slow motion. So at equilibrium, derivatives are 0 and coordinates are exactly Q0. So now we have nearby coordinates are nearby and velocities are also nearby 0. Okay, so what you can do in this case? So first of all, potential. So we need the potential. So we take Taylor expansion. Taylor at Q0. So this is now a function of many variables. So remember what is the expansion. So first is a value. The next term will be sum of the same way. So we call delta Q is Q minus Q0. The next will be sum of the derivatives. First derivatives by difference. And next term will be 1/2 of the ij. No, let's put jk. Second order derivatives. This is I. So jk. Second derivative computed at Q0. Delta Qj. Delta Qk. So this is Taylor expansion of first terms, second terms, as a function of many variables. Just Taylor expansion, first term, second term, and so on. Good, but this is 0. This is 0. Next, what we can do, we can just give a name. Remember, in 1 degree of freedom system, we gave the name C. So now it's Cjk. So we define Cjk as a second derivative of a potential at the equilibrium. So it's just number, but there are n numbers of this. So j and k, they change from 1 to n. So in fact, this gives you matrix. So that's C11, C12, C21, C22, and so on. So it's an n by n matrix. It's often called stiffness matrix. So we will call it stiffness matrix because we will see that it comes from elastic coefficients, but in principle it can be any other origin in physically. So it's stiffness matrix, and what is important in this matrix is that you see the derivatives commute. So it means that it is symmetric because Cjk is the same as Ckj. Yeah, because order of derivative doesn't matter. Or in the matrix form, it means that C equals C transposed. Okay? So we have this. Almost done. So now let's use all these properties. So we use that derivative is 0, and second derivative we call it C. So we now have a potential function in the form u q0 plus 1/2 sum jk 1 to n cjk delta qg q. And I put approximately because I want now to cancel I disconsider the rest. Because we're near the equilibrium, so the next other terms are much smaller. So we just keep those two. Okay. And we'll also, so the second step, we define also the matrix M, which is a matrix of Mij coefficients at the equilibrium. And this is also symmetric. It is also symmetric. Because we know that Mij equal Mji. Or it means that matrix coincides with its transposed. Okay, good. So now we take this equation and we make approximation near the equilibrium. I will write it down. That step is important. And that derivative of u with respect to the coordinates. So now remember that it's just the same computation as we did here. So what will be du? So what will you get here is you have to get the sum Cij delta Qj. So this is du dqi. So make it as an exercise. So if you differentiate this expression with respect to a component, you get this. It's just the same calculation as we did here on that line. You differentiate the product, first coordinate, second coordinate, so you have two sums, and then you use symmetry of the C matrix, so you get the same expression but with C. So this is 0. So what you can see that this you can approximate with this by values at Q0. So then it becomes first order term. So this is first order term. First order terms mean that it's proportional to the small values. So this is small. This is a second order term because of the product. And this is again first order term because it's linear in small quantities. So second order terms are much smaller than first order terms because if you take a product of two small values, it's smaller than the first. So approximately we can also neglect those terms. So now, you see, now we do it just on the level of kind of more intuitive level. So we just take terms which are much smaller near the equilibrium and just neglect them. But later, at that moment, we make this all rigorous. So this will be clear mathematical theory. But so far, let's do it in this way. So we can neglect this term because it's much smaller than both of them. Because these are first order, and this is a product of two small terms. Finishing. Just have to write the result. So then we get a result. So that's we have approximately this system. We can put delta here. That doesn't hurt. Plus. Is the same sum. And we can put a vector form of this equation. So this is true. This should be satisfied for all I. But if you see that this is an M matrix, this is C matrix. So you can just write it in vector form. M delta Q double dot plus C Q equals 0. So this is a matrix multiplied by a vector. Matrix multiplied by a vector. So this is the equation for approximate equation for oscillations near the equilibrium. The word approximate is also what we will use later. A more rigorous form is linearized. Linearized means that we only kept first order or linear terms, and higher order terms which are nonlinear, quadratic, cubic, we neglected. So this is the equation. So the properties of the equation is that M is a symmetric matrix and C is a symmetric matrix. So that's it. That's it. And remember, in the 1 degree of freedom system, what we had, the M was just our mass, and C was just that small c, which second derivative. So all what changed from 1 degree of freedom to n degree of freedom is that mass became a matrix, symmetric, and the C became also the matrix. So now we have the same equation, but in matrix vector with the vectors and matrices. So the question how to solve and what are the properties. So the equation, that's the first question, and second question, so this is approximated equation. So if we solve this equation, what we can actually what we can surely say about the full equation. Because this equation is not exactly equivalent to the full equation. It was obtained after some simplifications, just keeping the main terms. So these are main terms. So this is what we will do tomorrow.